Okay, this is a new video on fuel cells. Pause it and have a look at what slide everything's on, and the next slide is also a contents page. Okay. If we compare fuel cells with combustion engines or power stations and batteries, fuel cells are fuels. They're non-metal fuel molecules like hydrogen generally, methane or methanol, and they react in a combustion-like reaction with oxygen. So instead of the chemical energy being released as heat, like in a combustion engine or a coal-fired power station, the chemical energy is directly converted to electrical energy, which is like batteries. Fuel cells are more efficient compared to coal-fired power stations and batteries. No, it's not batteries. Combustion engines. All right. Fuel cells are more efficient compared to coal-fired power stations and combustion engines, I should say, and coal-fired power stations. So they're much more efficient at converting the chemical energy into electricity. But they're not as efficient as a battery, which is close to 100% efficient. So they do lose some heat. Fuel cells have fuels in them, non-metal molecules. Batteries use metals as their energy source, and they have a fixed supply of reactants, whereas in a fuel cell the reactants are added continuously, like in a car. So it is similar to a combustion engine in that respect. So the parts of a fuel cell look a bit similar to a battery. You've got an anode, which is actually porous, unlike a battery. So it's full of holes, which increases the surface area and allows the hydrogen molecules to absorb faster. It's also is platinum coated, or is made of platinum. The platinum acts like a catalyst and lowers the activation energy needed to break up the hydrogen so that it loses its electrons for electricity and makes hydrogen ions. The electrolyte is like a salt bridge in a battery. It's where the ions move to balance the charge, and the ions that are moving are produced by one or other of the reactants. So they're produced, hydrogen's produced, or hydroxide's produced sometimes. Sometimes they're already present. The chemical undergoing reduction is always oxygen. So you've got hydrogen or some sort of fuel at the anode losing its electrons, and then what's gaining them is always oxygen. So the most common reaction in a fuel cell, the most common fuel is hydrogen reacting with oxygen to make water. Pause this and have a read through it. The parts of a fuel cell, so the anode, the electrolyte and the cathode. The electrons are produced and move through whatever it is that you're trying to drive with the electricity. So if it's in a car, then this would be driving your car, making the wheels turn. And the ions move across. So we've got our fuel, hydrogen often, and our other reactant is oxygen. And water is the only thing that's produced. So if we concentrate on the anode, fuel cells are continuous. You don't recharge them, which is often a question in the exams. The anode, as I said here, this is the anode. It's full of holes. Hydrogen comes in. The hydrogen has to break, so we need to help that happen with a catalyst to speed up that the breaking of the hydrogen molecule to make hydrogen ions, which have lost their electrons, and the electrons that are produced moving from the anode through the car and back to the cathode. So this is our anode, which is full of holes. If we didn't have those holes to let the hydrogen, to increase the surface area for the hydrogen to attach to the electrode, then the rate of this reaction would be too slow. Yeah, the trouble with platinum is it's expensive. Anode. Now we're going to look at what makes different sorts of fuel cells, and quite often they're distinguished by the electrolyte that they've got. The electrolyte, as we said before, is like the salt bridge, allows the movement of ions to balance the charge, and it's often produced from the reactants. So with phosphoric acid fuel cells, the hydrogen produces hydrogen ions, and the oxygen's producing alkaline. Carbonate fuel cells are produced from oxygen and carbon dioxide, and oxygen in a solid oxide fuel cell. So these are produced from the reactants. Sometimes they're named after the fuel that's used. So a methanol fuel cell is using methanol, or you can have biogas fuel cells using methane. So if we look at the acid fuel cell in detail, so the electrolyte here is an acid. We've got our hydrogen, and we've already talked about it splitting and making electrons and hydrogen ions. The electrode won't allow the movement of electrons through here, so the electrons are transferred through the car or whatever is being charged. And the hydrogen ions that are produced are able to move. So the hydrogen ions are made over here, and then they move through the electrolyte, and they're used in the reaction over here with the oxygen. So hydrogen ions used with the electrons. The electrons have come over here and join to produce water. If you balance these two half equations, you would have to do this half equation twice, so that you've got 4 electrons being used, 4 electrons being produced. Put them, all the reactants together and all the products together, and then you cancel out the hydrogens, because it's 4 on both sides, cancel out the electrons, and you're just left with hydrogen and oxygen producing water. Okay, the alkaline fuel cell has the same setup. Hydrogen as the fuel, oxygen as the other reactant. Electrons are still produced at the anode, move through, used at the cathode. So everything's exactly the same except your electrolyte. So instead of having acid, you've now got hydroxide ions. Electrons' negative charge is leaving here, so the negative hydroxide would move across to this side to balance the charge this time. So if we've got hydroxide ions in here moving, then this side must have made the hydroxide ions. So in this case, instead of the oxygen reacting with hydrogen ions, the oxygen is reacting with water to produce hydroxide ions. These reactions are in your electrochemical series, but you can balance them anyway. So the hydroxide ions are moving across here, and in this time the hydrogen is breaking and still making hydrogen ions and electrons, but the hydrogen ions being made are immediately reacting with the hydroxide ions to produce water. So the overall equation is still, when you put these two half equations together, you would still get hydrogen and oxygen producing water. So you don't have to remember these equations off by heart. You should be able to balance them. If you know what's being produced and what's being used, you should be able to balance the overall equations. But these overall equations are in your electrochemical series. So the acid one, the hydrogen gas, is undergoing oxidation and producing hydrogen ions and electrons, and the oxygen is using the hydrogen ions produced here and the electrons, which have moved through the circuit and end up at the cathode, using these to produce water. If this was a 1 molar solution of everything, 1 atmosphere, standard conditions, then a fuel cell would produce 1.23 volts. If you use the hydroxide ion half equations, find that the difference between these is still 1.23 volts. So it's good to mark these on your electrochemical series so that you know that you don't need to balance them yourselves. You can just use what's in the electrochemical series and use the states that are mentioned. Okay, why use fuel cells? Why are we interested? Why is the world interested? There's two main reasons. The world's running out of hydrocarbon fossil fuels, so all your petrol, diesel, and when we burn fossil fuels, we produce carbon dioxide as a waste, which is contributing to climate change. So we need some alternative method of powering transport. So there's kind of a big battle at the moment. Batteries are winning the battle, and fuel cells are still kind of part of the equation. So if we looked at a hydrogen economy, so powering all our vehicles with hydrogen, ultimately we need to produce the hydrogen. So if we don't want to be making carbon dioxide, then we need to produce our hydrogen using renewable energy. So wind or solar or hydro can create electrical energy, and we can use that electrical energy to split water in electrolysis, which is chapter 9, I think, looking at electrolysis, which is like recharging, the recharging process of batteries, where you use electrical energy to produce a chemical. So we can add electricity to water to split it to make our hydrogen ions. Then we would have to transport our hydrogen gas, hydrogen gas around from wherever it's produced, so that we have, instead of petrol stations, we have hydrogen stations. So you'd go and fill up your car at a hydrogen fuel station, and your car would have a fuel cell, and your car would turn the chemical energy in the hydrogen back into water and produce electrical energy to drive your car. So the only product instead of carbon dioxide coming out your exhaust would be water. So the same sort of thing can apply to using batteries in your car. We need to have some sort of renewable energy to produce electricity, and we use the electricity to recharge your car battery. So you'd have to plug the car in, either at home or in a recharging station, plug it in somewhere, instead of a petrol station, you'd have to plug it in. And then it would force the electrons to go and recharge your battery, and then you can use your battery discharging to drive the car. So you'd have a battery in your car rather than a fuel cell, and it would work by discharging, so turning chemical energy into electrical. So either method, fuel cells or batteries, require that we have an infrastructure, that we build stations so that you can either refill with hydrogen or recharge your batteries. So far, fuel cells have been used or are being trying to be used around the world in quite a lot of countries. China is making a lot, Iceland, America. There's a lot of places that are trying to set up hydrogen fuel cell transport. Particularly, it's being trialled out with lots of buses. So these are all the places in operation around Europe at the moment, and all the places that are attempting to be in operation around Europe. I think Denmark is trying to be like the hydrogen supplier to the rest of Europe. China has spent nearly $60 billion so far subsidising its electric car industry with batteries, and now is spending about $13 billion on its fuel cell industry. So its companies are in partnership with other companies around the world, so American companies and European companies. They're buying shares of these companies and they're in partnership with them. About half of the electric cars and hybrid cars so far, the half electric, half petrol cars, are sold in China. So what to run transport on, batteries or fuel cells? So this is a little bit of a comparison. The costs: platinum's expensive metal for your electrodes in a fuel cell, but batteries also require lots of metals, some of them which are rare and have to be mined. Power to rate ratio, from what I can find, lithium ion batteries, you get about 100 watts for every kilogram of fuel. And the bus fuel cells, I found there was about 350 watts for every kilogram, so it looks like you get a bit more energy. There's all different varieties of this though, with different batteries and different fuel cells. I just picked these because it seemed to be the ones that we used. Refuel, so batteries have to be recharged, you have to plug them in and it takes time. Presumably refueling a fuel cell is quicker. Infrastructure though, if you want to have an electric car, we already have an electricity network, so you can just plug it in at home and recharge your car, whereas we would have to build hydrogen refueling stations. Hydrogen's a flammable gas, so it's flammable, could react with oxygen and explode, and it's a gas, so it needs to be kept in containers for transport, containers for storage. The container in your car has to be able to withstand the pressure. So there's fors and against for both. I think having a higher energy per kilogram is possibly why buses are using it. Some of the other advantages of fuel cells, obviously, rather than using petrol, you're not producing carbon dioxide. If the hydrogen or the fuel is produced by the electrolysis of water. So if the fuel is produced by fossil fuels, then there's no advantage with carbon dioxide. It's a method of storing renewable energy. So if you've got processes that like wind, solar, or hydro, the wind might blow one day and not the next, or you might have a lot of sun one day and not the next. You can, while the wind's blowing, you could be making hydrogen gas, and then when the wind stops, you could be using a fuel cell to produce electricity. They seem to have a higher energy to weight ratio than batteries. Disadvantages: it's flammable gas, dangerous, pressurized containers. There's not enough renewable energy produced at the moment, so hydrogen is often made by methane, CH4, and so carbon dioxide is produced anyway. It's just a table. If you pause it, you can write down some of the things we've talked about and put them into headings of comparison between batteries and fuel cells. Okay, past exam questions. The energy released in a chemical reaction is directly converted to electrical energy in A. So just pause it. I'll wait for 5 seconds and then I'll tell you the answer. Okay, so it's chemical energy to electrical energy. Chemical energy in a hydrogen fuel cell is directly converted to electrical energy. This is converted to electrical energy, but it's not chemical. Electrolytic is the opposite of producing energy. It's using electrical energy to produce chemical. It's the opposite. Fossil fuel power station. You are turning chemical energy in a fossil fuel like carbon into electricity, but you're not doing it directly. You're turning it into heat first and then losing a lot of the energy as heat. Okay, so answer these questions and in 5 seconds I'll give you the answers. Okay, a natural gas-fired power station generates electricity by reacting gaseous methane with oxygen. List in order the energy conversion process that takes place in the power station. So this is like a coal-fired power station, but it's natural gas. So the chemical energy in the methane, it's burnt and produces heat, and then the heat turns the turbine, which produces electricity. So there's energy lost as the heat energy that happens all the way along here is lost, which means that less electricity is generated by burning methane in a gas power station than if the same amount of methane were used in a fuel cell, because a fuel cell is direct conversion. So more energy is lost in greater amounts than a one-stage process. Oh, that's very clunky. In a fuel cell, it's directly chemical to electrical. And whoops, the previous question. State one factor that limits the widespread applications of fuel cells to generate electricity. They're higher cost because of the electrode being made out of platinum. All right. A fuel cell can be constructed that uses the following two half reactions. Okay. If they ever give you half equations on the exam, be really, really careful that they haven't swapped the order. So it needs to be like the electrochemical series. If you're going to use it with, assume that the higher oxidizing agent is above and the higher reducing agent is below. As you can see, they've swapped these because this is a higher voltage than that one. I get easily confused, so I would actually have to write it out. So I've removed this and put it in the proper order as it would be in the electrochemical series. So because it's up here now, then this is the stronger oxidizing agent, the oxygen, naturally, and this is the stronger reducing agent, the methanol. So the question is, which one of the following would occur at the negative electrode of the cell as it generates electricity? So when it's acting as a galvanic cell. So electricity is spontaneous galvanic. The anode is the negative electrode. Anode is negative when it's spontaneous. So anode always undergoes oxidation. Oxidation is the loss. The reaction that's losing electrons is this reaction. It's producing electrons. So hydrogen ions are being produced as well. So it's A. Which one of the following statements about this fuel cell is most likely to be correct? Okay. An external power supply is used to recharge the cell. No, you can't recharge fuel cells. Batteries are recharged. Fuel cells have a continuous supply of reactants, so you don't recharge them. Gaseous products are recycled into the cell to improve efficiency. No. The products, example, on the water, it's generally water, are released. Chemical energy is not completely converted into electrical energy. Yep, the chemical energy is not completely converted. Fuel cells are about 60% efficient, so there's a lot of there's waste heat energy also produced. So naturally, the last one's no. More hydrogen ions are produced at the anode than are consumed at the cathode. I think this was tempting for people because if they realised that this was the anode, if they'd swapped them round and they realised this was the anode, then they would have seen that there were more hydrogen ions here produced than at the cathode, and that one would have been really tempting. However, when you balance the electrons and make the overall equation, the number that both of these will go into is 12. So you'd have to double this equation and triple that equation. And when you do that, you'll find that you also make 12 hydrogen ions produced and consumed. So when you do the overall equation, it's the same. Okay, so this is the 2008 exam. Classic fuel cell, acid, electrolyte. Give the equation for the half reaction that takes place at the anode. Anode, oxidation. Anode is always oxidation. And oil, oxidation is the loss. So oxidation, which one of these chemicals is losing the electrons? We know it's the hydrogen. So it's just the classic hydrogen equation. Don't really understand why. This was for the 2 marks here for the oxygen as well. The oxygen half equation, it's on the electrochemical series. It's a hydrogen fuel cell. You just have to find the reduction reaction for oxygen and write it down. So I'm not really sure why 37% of people couldn't get any marks for that question. Alright, on the diagram of the fuel cell, draw an arrow to show the direction in which the H2PO4- ions move as the cell delivers an electric current. So if electrons are coming from here and going over to here, there's a lack of negative charge over here, so the negative ions will move in this direction. The negative ions are anions. The anions move towards the anode. Okay, so this was a half-half question. Not sure why this was so badly scored either. 2011 exam, a Victorian company produces solid oxide fuel cells for use in the home. These fuel cells use natural gas is methane, to produce electricity through an electrochemical process summarized in the diagram below. This is a really bad idea for a fuel cell, really. Well, it's better than burning the methane because you don't lose energy as heat, but you're going to be making carbon dioxide. Alright, so we've got oxygen here, oxide ions moving across. So suggest one way in which a fuel cell differs from other galvanic cells. So there's a lot of ideas that you could put there, and we just talked about some of them previously. So pause it and write down some ideas. So some of the ideas: fuel cells require a continuous supply of reactants, whereas, and if they ask for, you have to compare between one thing and another thing, you have to really get into the habit of referring to both of them. So whereas in a galvanic cell, they're stored in a set amount in the cell. So in that case, galvanic cells can be recharged, but fuel cells you don't recharge. So they said here you needed to be careful if you used the term rechargeable when dealing with electrochemical cells. It was only acceptable if it was cleanly used in reference to maintaining the supply of reactants for the fuel cell. So if you mention the fuel cell at the same time as saying that this is rechargeable, you would have to say that you couldn't recharge this because it had a continuous supply of reactants. So other things, products are removed from fuel cells. The fuel cells' electrodes are porous. They have a catalyst, which I guess galvanic cells could potentially have catalyst. Yeah. Write an equation for the reaction at the cathode when atmospheric oxygen is converted to oxide ions. Okay, so there's been no mention here of water or anything else to use, any other hydrogen ions. It's talking about atmospheric oxygen, and it's only saying that oxide ions are produced. So a lot of people would probably have been trying to balance this with water and add hydrogen. So it's an unusual question. When you're doing this, you need to remember, if you've got oxygen, each oxygen molecule is sharing 2 electrons with another oxygen molecule. Each oxygen molecule would gain 2 electrons, each oxygen atom, I should say. And you've got 2 oxygen atoms, so each one of them is going to gain 2 electrons. So you would need 4 electrons. So they're saying here that a lot of people didn't balance it with the 4. And then this question here, this one here, has also not balanced the individual atoms. So you have 2 oxygen ions. So be careful. So it gives you this equation. A complex series of reactions takes place at the anode. So you don't have to balance this. And then it asks you to write an equation that represents the overall. So the overall is basically a combustion reaction. We've got methane, we're adding oxygen to it. It's a combustion reaction like the other hydrogen plus oxygen. It's making carbon dioxide and water. So you can just write a combustion reaction as your overall. You could put the 2 half equations together, and when they all cancelled out, you would end up with this equation as well. Okay.